All right, now, although it's not part of the course, you might be interested to see the proof from first principles that d by dx of log x, the natural log of x, is of course 1 over x. Now we can do this using a key ingredient, which is the definition of E. And it's the definition you don't see very regularly, particularly at A-level maths, but it's a definition nonetheless. So I'm just going to write it down. And it's the definition of E based on the principle of compound interest, essentially. So it's the limit as n approaches infinity of the following expression. So it's 1 plus 1 over n raised to the power n. Okay. Now, how does this definition work? Well, I'll just give you a couple of examples, and I'll show you on an Excel spreadsheet later on in the video. So if you let's say n equal 1, okay, what we have is that the expression that's not being limited in a sense. So this expression here, if we substitute n equals 1 into that, well, what do we get? Well, it's quite easy to do the substitution. We're going to get 1 plus 1 over 1 all raised to the power 1. Okay, which is just going to be 2. Okay, now if you know anything about E, it's approximately 2.71. Okay, so it's an irrational number, hence that's why we take a limit as n approaches infinity. Okay, it's not a decimal, that is a fraction that we can write down. Now, if we put n equals 2 in, okay, I'll just do a couple of these. So we get 1 plus 1 over 2 this time, raised to the power 2. So it's the power is inversely proportional to the amount added on to 1. Okay, so if you're adding on a half, then you raise it to power 2. And similarly, if n was 3, it would be 1 plus a third raised to the power 3. Now, if you do that, you're going to get 3 over 2. So it's 1.5 squared, which is, of course, 9 over 4, which is 2.25. All right, so the argument is that as n approaches infinity, the value you're going to get as it starts at 2 is going to approach 2.71 E. Okay, and it seems to be approaching it from below. So it's a lower limit. So just to give you an idea of how E behaves using this definition. So I've set up a column here. So these are the n values. So natural numbers 1 up to infinity. Okay, not counting infinity as a number, of course, it's not. And then the expression 1 plus 1 over n to the power n. So we've done the first one. We did the first two as part of the lesson. So if I just extend that, so obviously if you put in 2 for the natural number, so that's 1 plus 1 over 2, which is 3 over 2 raised to the power 2, which is 2.25. Now the difference between E and that value, it has been reduced, so it's just less than 0.5. Now, if you'll bear with me, I'm just going to continue this, and then we'll go up to 30, and we'll see how close we get to the value E, which I've got here, to 9 decimal places. So if we just go down to maybe 30. Okay, so we're at 2.67. We're closing the gap. We're now in the hundreds. So about 4 hundredths away from the, I say exact, but the value that we've got at the top of the table. Let's go down. Let's go down to over 1,000. Let's see. So about 1,300 there, nearly 1,400. So the gap is obviously closing. We're getting closer and closer to E. We're now in the tens of thousands now, and we can continue this even further. Why not? So I'll extend it down even further. We'll stop there. So 2,700, and the gap is closing. It's not accelerating towards E, but it's quite a slow progress. But it's pretty clear that as we get as n approaches infinity, we are getting, of course, closer and closer to e from below. All right, so that's one way that e is defined using a limit like that. Taking this definition of e, what I'm going to do, just before we start writing the proof from first principles, I'm going to take the log of this definition. Now, we know that the natural log of e is, of course, 1. Okay, so if I take the natural log of the left-hand side e, which is clear, okay, we know that's equal to 1, but it would be the same as taking the natural log of the right-hand side. So I'm going to do that as well and see if we can do anything with this. So I'm going to take the natural log and I'm going to open big square brackets here because I've got to take the natural log of the whole side. Remember, it's a function. So it's the limit as n approaches infinity of 1 plus 1 over n raised to the power n. And I'm going to close those big square brackets. Right. So you might be thinking, what is the point of this? Well, we know that the right-hand side is equal to 1, okay, in the limit. But the good thing about limits is that limits are linear in the same way that a differentiation is a linear operator. And that means I can interchange the natural log and the limit, okay? And the other thing about limits is that they will only apply to the terms which contain n in this case, okay? So, for example, the 1 in this expression here will not be affected because it doesn't contain an n, okay? However, the 1 over n and the n obviously will be affected by the limit. So what I'm going to do next is I'm going to swap the limit and the log around. All right, so we can swap the limit and the log around. So I'm going to have the limit of the natural log of 1 plus 1 over n to the power n, and we'll put those in the brackets. So we've got something we might be able to work with. Now, this is going to be an important result, so I'm going to call it a noun. I'm going to call it star. So we might be coming back to that later. And remember, of course, that this value is equal to 1 because that's the natural log of e. Great. So what we're going to do now is we're going to do the derivative from first principles. So I'm going to define my function as the natural log of x. So we're going to say let f of x equal the natural log of x. Okay, and we know from the definition that f dash x is equal to the limit as h approaches 0 of f of x plus h subtract f of x all over h. Okay, so now we just substitute our function natural log of x into that definition. So I'm going to just carry on down here so we've got a bit more space, and I'll just partition the board. So there we go. So the derivative f dash x would be equal to the limit as h approaches 0. Now then, if we substitute in x plus h into our function, as you can see here, in my function, I just replace the x wherever I see it with x plus h. So that's easily done, isn't it? So the function is, of course, the natural log. So it's going to be the natural log of x plus h. I'll just put it in red so you can see what I've done in this step. Subtract the natural log of x, which is just f of x, isn't it? All over h. So that's the first step. It's just a case of substituting in the function into the definition. What can we do with this? Well, if you know anything about logarithms, you'll notice that in the numerator we have the difference of two logarithms Both the logarithms have the same base, which is e. So I can actually write the numerator as a single logarithm, okay, as follows. So this is going to be equal to the limit as h approaches 0. And as a single logarithm, it's going to be the natural log of x plus h over x, like that. And then the denominator is, of course, going to be h. Okay, so that's what I've done to the numerator. So I've just applied the laws of logarithms there. Okay. So what can we do with this? Well, I can rewrite the expression inside the brackets, but I can also remove the fraction element of this limit in its entirety. And what I should probably be doing is putting some brackets around all this. So it's clear. Okay, so let's do that. So next step, I'm going to just do a little bit of rewriting here. I'm not going to do anything drastic. So I'm going to take the limit as h approaches 0. Remember not to drop that step. It's really important. I'll put my brackets in now. So rather than having a h in the denominator, I'm going to write this as 1 over h multiplying the numerator, essentially, which is the same thing. It's the same way of writing it, or it's the same principle, I should say. So this is going to be the natural log of whatever's inside the bracket. Now, you'll notice as well, inside the bracket, we've got x divided by x. Okay, so I can actually rewrite that as 1 because it's x over itself, so that simplifies to 1. But in the second term in the numerator, I'm going to have h over x, as you can see there. So that's going to be 1 plus h over x. Okay, I'll just close that. And I'll just close the big green brackets, the big square brackets. And I think it'd be a good idea. I'm just going to remove that so we can see it clearly. So I've rewritten x plus h over x as 1 plus h over x as 2 terms. Now then, you may start to notice we've got our expression star on the left. There is a similarity, isn't there? They're starting to look quite distinct. Now, quite similar. Now, the one thing you will notice that there is a difference is the 1 over h at the front is causing an issue, isn't it? It's not a feature of star over here. There's nothing multiplying the logarithm. But because this is a logarithm, we can actually do something with 1 over h. Another element that is missing is the fact that we have an n as a power, and we don't have any power here. But we can solve this in one step, because the laws of logarithms state that if I have a coefficient multiplying the log, I can move its position so that it is actually a power. Okay, it's the power law for logarithms. So it's the limit as h approaches 0 of the natural log of 1 plus h over x. Okay, and then I'm going to move that coefficient into the power position. So it's going to be 1 over h as a power, and we'll close the brackets as well. Right, so we're getting closer to this magical star expression. So what now is the difference? Well, you'll notice as well that in the expression we've got, that we've just been working through from the definition of the derivative, we have h over x here, which is comparable to the 1 over n here. They're analogous, aren't they? Okay, they should be the same thing. And we've also got 1 over h in the power, which corresponds to n. Now, what we could do is we could make a clever substitution. So I'm just going to do this work in the bottom left-hand corner over here. So I'm going to say, let 1 over n equal h over x. Okay. So if I do that, if I just say, okay, h over x and 1 over n are the same, I can make the swap here, okay? And then I'm going to have the natural log of 1 plus 1 over n, which is what I wanted. But I've got to make sure that this doesn't interfere with what I've got in the power. And what I mean by that is I'm not going to get something that clearly just disproves the whole thing. So what I'm going to do is I'm going to also have to find out what 1 over h is equal to as well. So this implies that x, or let me do that again, that h is equal to x over n. Okay, that's what that substitution implies. So therefore, 1 over h would simply be the reciprocal of that, which would be n over x. So what I'm going to have to do is, there is some disruption here. I'm going to have to replace my 1 over h with n over x. I'm forced to do that by the substitution I've chosen. So although it solved a problem inside the bracket of the logarithm, I've now got a problem in the power, okay, that I'm going to have to deal with. Something else we should notice as well is that if I'm replacing h's with n's, what happens in the limit? So what will happen in this part of my expression as h approaches 0? Well, we can see clearly that h and n are inversely proportional to each other. So from this expression here, we can, or this equation I should say, as h approaches 0, that would mean that n would have to approach infinity. Okay, now I think that is clear from that equation because they are inversely proportional. So another important result there. So I'm going to put all these ingredients together into the next step of our derivative. So what do we have? We're going to have the limit. Now, if h approaches 0, then I can replace that with n approaching infinity because it's the same process, because the h and n are inversely proportional to each other. I'm going to open the square brackets now, and we've got the natural log. Okay, now I'm going to replace my h over x with 1 over n. So that's going to be 1 plus 1 over n. So it's starting to look good. I've got almost all the ingredients that I wanted. Okay, so I've got the limit as n approaches infinity. I've got the 1 over n inside the bracket. My only problem now is that my 1 over h in the power is now going to be replaced by n over x, as we can see, or as we saw in this step here. Okay, so I'm forced to do that, otherwise I'd be inconsistent and just wrong, to be blunt. So this is going to be n over x. Okay, so this is where I'm at with my derivative. Now you'll see something else. We've used the power law already. Now the thing that's causing the problem is the fact that it's not a loss really. Okay, it's not a complete loss because I do have the n in the position that I want to here. Okay, so I do want to raise 1 plus 1 over n to the power n. The problem is the denominator. But what I can do is I can use the power law again for logarithms. So I'm going to go up to this side, and we're going to say all this is equal to the limit as n approaches infinity. Let's open those big square brackets again. And we're going to have the natural log of, let's just get rid of that, sorry. So I'm going to bring the power down now, but I'm not going to bring the whole power down. I'm just going to bring down the 1 over x part. So the 1 over x is going to come down to the front. And I'm going to have the natural log of 1 plus 1 over n. And what I've got left in the power is just the n. Like that. Okay, so just check that you're following that step. So I'm just bringing down the denominator part of the power, the 1 over x, using the power law, and it becomes a multiplicative factor at the front of the logarithm. Okay, what happens now? Well, we're talking about limits earlier, weren't we? And some of their properties. Now, if you'll notice, we're taking the limit as n approaches infinity now after our substitution. So this means that anything containing n, such as this and this, we're going to have to take the limit. Okay, but what is not affected by this limit is the 1 over x. There's no n element in that whatsoever. There's no n factor at all. So I can use the property of limits. So I can now factor out the 1 over x because that will not be affected by the limit at all. So I'm going to do that. So this is going to give me 1 over x. So let's put it all to the front. And we're going to set up the brackets again. So that's going to be the limit as n approaches infinity of the natural log of 1 plus 1 over n raised to the power n. Like that. Okay. Now, this is where we're really in business. So we've seemed to have got everything on our wish list now. And you'll notice, if I just highlight all this, what have we got in here? We've got the limit as n approaches infinity of the natural log of 1 plus 1 over n raised to the power n. Well, that's exactly what we've got here. Okay. So we finally have star. Okay. We've finally got to that step. And you'll notice that the only difference is that we've now got a factor of 1 over x at the front, multiplying the whole thing. So because I've got that complicated looking expression and I know it's just equal to 1, so this is going to equal 1 over x multiplied by 1. Okay, by the work we did earlier. Okay, so that's why that definition of E is so important. Okay, so our final answer is, of course, that the derivative of the natural log of x is 1 over x. Okay, so that concludes the proof.